Next up, I'd like to welcome Jo Howes to the stage, the virtual stage, I suppose, who is a principal consultant for E4Tech.
So, hello everybody. I'm from E4Tech, and I'm here to talk about how do we make sure that that hydrogen that's supplied to all of the uses that Colette talked about and to Brian's buses is low carbon, and what are the ways that we can do that, and how do we make sure that it happens? So, as a quick introduction, E4Tech is a sustainable energy consultancy based in London and in Lausanne in Switzerland. And we've been working on hydrogen and fuel cells, as well as other energy systems questions and low carbon transport generally for over 20 years. We also publish annually the Fuel Cell Industry Review, which is the leading annual review of what's going on in fuel cell markets and numbers of shipments and things like that. So you can download that if you're interested in some more data behind hydrogen and fuel cell deployments in the transport sector. Now, one of the areas that we look at a lot is the sustainability of these different options. And so that's what I'm going to be talking about today. So as Brian's just been discussing, we're talking about hydrogen in this forum today because there are lots of advantages of hydrogen fuel cell vehicles amongst all of the other options that we've got for decarbonising transport, which vary quite a lot depending on what mode you're talking about, the size and weight of a vehicle. And I just put in a graph here from the Hydrogen Council that showed where they see hydrogen fitting within the suite of low carbon options that you could have for different technologies. So lots of advantages to using hydrogen. But the question is, how do we make sure that we're getting the best options that we can from an environmental perspective? So the way that we look at this typically is through life cycle analysis, shortened to LCA. And this is a way of looking at all of the impacts of providing a service, in this case, transportation, driving a car a certain distance. And life cycle analysis takes into account all the parts of the life cycle of doing that. So what does it take to produce the vehicle? What does it take to produce the fuel? What are the impacts in using that fuel? And what are the impacts in the end of life of the vehicle? Now, you can do this across lots of different impacts. You could do it across water use or air pollution or all kinds of different things. But today I'm mostly going to be talking about greenhouse gas impacts because this is the key challenge really when we're talking about different hydrogen production routes. So we and others have done life cycle analysis studies that look across different types of vehicles. This is some analysis that we did in 2018, looking at different types of cars and looking at the greenhouse gas emissions, which are expressed in grams of CO2 per kilometre up here, and looking at how much of those come from producing and disposing of the vehicle, how much of those come from fuel production, how much come from actually using the fuel, carbon dioxide that comes out when you burn fossil fuels, for example, and how much comes from vehicle maintenance. I'm not going to talk through all of this, because I only have 10 minutes. The important point that I want to make is that for most of these different types of vehicle, most of the emissions are related to the fuel itself. You can see that from looking at the mid-blue fuel production and fuel use parts of these bars. And if you look at the area highlighted in green, which is the fuel cell electric vehicles, you can see that the numbers vary hugely. And the reason that these numbers vary hugely is due to this mid-blue fuel production bar, where the way in which you make the hydrogen has a huge impact on the greenhouse gas emissions. So Colette talked a bit at the beginning about the different ways that you can make hydrogen, and there are many different ways to make hydrogen. If we draw a spider diagram of all the ways that we've thought about it, looks very, very complicated. So just as an overview, there are 4 ways that I've put on this slide, which include some of the ways that Colette was talking about. So you can use fossil fuels. So for example, natural gas splitting that to produce hydrogen, and electrolysis, using renewable electricity. They're typically the two main ways that people talk about. But importantly, there's also byproduct hydrogen from existing industrial processes. And there's also the option to produce hydrogen from biomass, or even waste. So as I was saying, lots of different ways to produce hydrogen. This is a graph made by LBST, another consultancy who did this study for the Hydrogen Council, that just shows the range of emissions factors that you can get depending on how you produce hydrogen. And this is only how you produce it. And as I said, a UK specific study on this that we've done together with LBST will be coming out later this year that we've done for BEIS. But the important thing is that these purple boxes on the left-hand side, these different ways of producing hydrogen, you can't make generalizations about those and say, well, this one's better than that one, because there are lots of different, very specific details of what the supply chain looks like for hydrogen, where it is, when it is, that really affect these greenhouse gas emissions. So a few things to bring out is use of grid electricity. Now, obviously, this is most important if you are running an electrolyzer off grid electricity, but it's actually also important for lots of other parts of the chains, compression, and electricity use in any of these other chains, that if you are using grid electricity, then the difference you can see here between 2030 and 2050 is huge, as grids decarbonize. And obviously the grid electricity factors between countries vary hugely as well. As Colette talked about, if you're going to enable blue hydrogen routes, if you're going to enable use of fossil fuels, then you need CCS. And you can see the big difference between these routes at the top, which are fossil without CCS, and those that include CCS that are down here. The ones at the bottom are typically renewables and nuclear routes that give very low greenhouse gas hydrogen results. And also biomass feedstocks give pretty low results, but that can vary quite a lot depending on the source of the biomass that you're using. Also, something that we've modeled in our study for BEIS, but is not modeled here, is routes that end up with negative emissions. And that could happen if you have a biomass route where effectively you're gasifying the biomass and taking the CO2 and sequestering it, and then using the hydrogen. And if you store that CO2 permanently, then effectively you've got a negative emissions route. You've got something that's providing hydrogen as an energy carrier and also providing a carbon sink. But, as mentioned before, this is an end-to-end system. Production of the hydrogen is not the end, it's the beginning. And there are lots and lots of different ways that hydrogen could be used in different sectors. And to get it from the point of production to the point of use, there could be a whole range of different downstream options to do with how you transport it, whether you compress it, to what extent you compress it, whether you liquefy it, how pure does it need to be, whether you convert it into a different kind of energy carrier like ammonia. And all of those have emissions. And emissions from some of these could actually be larger than the production emissions itself, depending on which production pathway that you've used. So there are big variations in these factors to do with, as I said, whether you liquefy, how much electricity you use in this process, how far you transport, but there are also quite a lot of uncertainties. So, if you put hydrogen through a pipeline, what contaminants does it have? And therefore, what do you need to do to purify it to use it in a vehicle? So I don't want to scare you all by these slides of saying there's a huge variation here, because these things are measurable and in lots of cases are manageable. But it's just important to do that to ensure that we get the savings that we want. And as you'll have seen, even the graphs that I've shown don't give you the same results for the same pathway. You can only do this by having a common methodology. And typically those common methodologies are codified in standards, and those standards are used to underpin various activities to make sure that we get the savings that we need. So there are voluntary standards that have been developed. So one of them, most high profile ones at the moment, is Certify, which is a voluntary scheme which is a guarantee of origin for green or low carbon hydrogen in Europe. In the UK, we also have policy that does this. So we have the renewable transport fuel obligation, which incentivizes use of renewable fuels, and hydrogen can count towards that. So renewable hydrogen can receive credits under that scheme as long as it meets sustainability criteria, including 60% greenhouse gas savings, though there's actually a consultation out on increasing that to 65 at the moment. And as we see more hydrogen use across the economy, there may be other policies developed that help to support hydrogen use across other sectors. And then you've got to work out how we develop a low carbon hydrogen system that works for everybody.